One of the problems we have in most circumstances is finding the correct antiderivative. As we saw, we already opened up a huge pile of different methods we can use, and we arrived at lots of different options. And here are two problems I don't know how to do. The one on the right might have a formula. Said formula is not in our textbook. And unfortunately, in a fit of stupidity, I took the other two tables out of my box. So I didn't bring them with me today. And that means I'm screwed. I don't know how to do this problem. The one on the left actually has no antiderivative. If I try to do this, I cannot write the answer in terms of functions we already know and understand. Trying to solve this problem algebraically results in something called a non-standard integral defined function. I don't actually get an antiderivative that makes sense the way we write those functions. As a matter of fact, if you've got your computer or your technology in front of you, you should go to Wolfram Alpha and try and do that first integral. The integral of e to the x squared dx, and tell me what it gives you. I think the version I looked at last time said something like EI of x, capital E, lowercase I, as an elliptic integral of the first kind or something like that. On the other hand, I'm not actually asking for the antiderivative. The problems I want to do, top of that page, are definite integrals. And I know that the fundamental theorem of calculus says to do a definite integral, first you do the indefinite one, and then you plug in and do f of b minus f of a. But that only works if I know what capital F is, and I don't in this case. So let's roll back the clock. What did we do before the fundamental theorem of calculus? What do you got, Leo?
I was thinking like you can maybe do that like on a calculator, where you do like approximate like n number of approximates, like if there's like 5 would be like 5 between 1 and 3.
Aha! Before we did the fundamental theorem of calculus, we did Riemann sums. Now, the problem with doing a Riemann sum was that we had to do that limit as n went to infinity, but that was to get an exact answer. And if I don't want an exact answer, I can approximate. And if I approximate, well, then I can figure out how many rectangles I need to get a good approximation. Okay. What I need to decide what I'm going to use to determine the finite number of rectangles, and then whether I'm going to use the left edges, the right edges, the midpoints. I have all sorts of options here. So if we're going the integral from 1 to 3, e to the x squared dx, I need to figure out how to break that up. Doesn't matter how many integrals I use, how many intervals I use, we just have to decide. And then we'll see how close we got to the quote unquote right answer. It's a reasonable number. How about we use, how about we use 10 of them? So I've got x0, x1, x2, x3, x4, x5, x6, x7, x8, x9, and x10. Now we have to make a decision. If I do the left edge of each of these, then I'm really going to use 0, 1, 2, 3, 4 through 9. The reason I wrote I minus 1 there is because I numbered my rectangles 1 through 10, but I want to use x0 for the first one, and x1 for the second one, and x2 for the third one, and so on. And this would give me the left edge as the height. So the height times width. Add up the rectangles, and you're done. How does that formula change if I want to do the right endpoint?
It'd be I plus 1.
Unfortunately, no. That's very close, but it wouldn't be, because if I'm looking at this first rectangle, then I want to use x1, right? And if I'm looking at the second rectangle, I want to use x2. So instead of being I minus 1, it's just going to be I itself. Now, how do we find delta x? All the way back in chapter 5, where we did this the first time, we had a formula for delta x. How wide are each of those little pieces in that section? Dom? I thought you were yeah.
Maybe 0.2.
How?
It's like it's between 1 and 3, it's going to be 2, but then it's cut by 10 pieces. They're each be worth 0.2.
So for our example, you're right, it's 0.2. In general, we figure out how long the section is from A to B, that's B minus A, and divide it into all those n pieces. Out comes the calculator. And if I'm doing this as an approximation, I'm going to get approximately equals. I'm going to write out the sum. This step is optional, but I think it will help us. We're going to have f of 1, that's x0, and then f of 1.2, and f of 1.4, f of 1.6, f of 1.8, f of 2, f of 2.2, f of 2.4, f of 2.6, and f of 2.8, and all of that is multiplied by the width of our interval. When I do the sum, I add, and then I multiply at the end rather than multiplying each one. Now this is our left sum. So I'm going to call this L10. And now I can actually do this sum on here. But in order to do the sum, I need the values for all of those. So I graph e to the x squared. I need to know what's going on between 1 and 3. This graph gets really big really quick. The y-axis here goes from 0 to 10, and we shot off the top really fast. But I can hit the trace button, and I can start putting in the numbers I want. Notice that when x equals 2, I'm at 54.6 already. So if I really wanted a better window, I need to go much higher. Window now goes up to 250, and I still blow off the top before I get to 3. This is huge. But I can get all these y values in 2 different ways. I can use the trace button, trace, put in 1, put in 1.2, and so on. Or I can go to the table. Above the graph button, it says table. If I want to use the table, though, I need to set the table. Above window, it says table set. So I hit second and window to get to the table settings. And I'm going to tell my table to start at 1. And I'm going to tell it to step delta x, 0.2. And then instead of having ask highlighted, I'm going to tell it auto. Just by hitting enter, it'll re-highlight. Yours is probably set to auto. I had it for ask for another class. But now, if I go to the table, it'll start at 1, and it'll generate all of the y values that I need. And I can just scroll down that table and copy all these numbers over. It's not short, is it? By the way, how does this change if I want to do the right sum? Right, I'd start at 1.2, I'd still step up by 2, and my last one would be f of 3 instead of f of 2.8, and I'd lose f of 1 at the beginning. Questions? I believe if we actually do this, the answer is around 1400. I'm sorry?
Like when we did the quiz.
I'd want a decimal, right? Because in this case, these numbers get ridiculously large very quickly.
No, I'm saying, do you want to say?
Oh no, I'd want numbers in here and you could do all the adding and finish out the arithmetic. I just haven't done that yet. All right, you want to do R or L? I don't care which one. Which one do you actually want to do? L? Okay. That means I go back up here and I start at I go back up here and I start at 1. Now we have to make another executive decision. This will usually be in the problem itself. It'll tell you how many decimal places to keep. I'm going to keep 4. The reason I picked 4 is because it's what's showing in this column. To 540.2048. Now I got to add all that crap up inside that parentheses. Divide that by 5. Or multiply by 0.2, right? 800. If I were actually asking you to do it, Jacob, that would be what I wanted. Get all the way to the number. Is this an underestimate or an overestimate? How do you know? It's our graph looks like this. From 1 to 3, it goes like that. Since it's concave up, what is true? That it's an overestimate. Well, wait a minute. I'm using the left edge for each of these, right? So let's think about that first rectangle. That first rectangle has as its height this left side. The second rectangle has as its height, we came in under. The third one, under. Okay, wait a second. I think this is actually going to be an underestimate. And since this graph gets really big really fast, we're missing a bunch of area, aren't we? If I did the right side, how would that picture change? Yeah. Right, because each rectangle would stick out a little bit above, right? I'd get these little corners outside. But in this case, it's not because the function is necessarily concave up, but it's because it's increasing. The left side will be lower than the right side. And all that tells me is that the actual area is somewhere between those two numbers. I've only calculated one of them. I could calculate the other one and get an upper bound and a lower bound. But again, because this particular function got really big really quickly, I'm not sure either of these are going to be particularly accurate. How could I get more accurate? I could do the midpoint, right? Halfway between the low and the high, be the middle. Well, technically halfway between the low and the high and the x would be the middle. But let's take a look at what that looks like. The midpoint sum I didn't actually write xi or xi minus 1. How the hell do I do xi star? Well, I have to pick the middle, right? So I take the two of them and I average them together. Halfway between xi minus 1 and xi. And that would absolutely work. Oh, I want to call this m sub n because it goes for n rectangles. So if we did m10, we'd use 1.1 and 1.3 and 1.5 and so on. But that's another sum, right? I'd have to do a whole other set of calculations. If I already have a left and a right, and one's under and one's over, I might be able to average those. Now, it turns out that this actually does give me a nice geometric picture. Let me zoom in on one of the rectangles. So there's the one where I get ln, and there's the one where I get rn, right? I have the underestimate and the overestimate. And if I average those, that would be the same as averaging these two y values. So that rectangle, its left short piece would be f of x I minus 1. Its right piece would be f of xi. And its width is delta x. Wait a minute. If I average those two areas, isn't that the same as cutting this little rectangle up here in half? Instead of cutting it in half horizontally or cutting it in half vertically, I'm going to cut it in half diagonally. Notice that the little diagonal line, the curve is slightly under it in this case, right? but it's a much smaller difference than either the difference between the small rectangle in the curve or the big rectangle in the curve. But that means that my new shape isn't a rectangle anymore. That shape is a trapezoid because the left side and the right side are parallel to each other. When I do this, instead of adding up rectangles, I can actually think of it as adding up trapezoids. Yes, but that's exactly what my trapezoid does. Here's the fun part. What's the formula for the area of a trapezoid? Well, the area of the trapezoid averages those two sides and multiplies by the width, which is exactly what ln plus rn over 2 does. It adds them together and divides by 2. Well, wait a minute. Formulaically, we were adding a bunch of stuff up, right? Let's go back and look at our left 10 and our right 10. L10 started with 1, right? We did f of 1, f of 1.2, f of 1.4, and so on until we got to f of 2.8, and we stopped. The right sum started with 1.2, 1.4, 1.6. Those are the same numbers again, aren't they? Until I got to 2.8, and then we did 3. A way to think of a trapezoid sum is to say you only want one of the very first point, one of the very last point, and then you want 2 of everything else, and then you average and multiply by delta x. This is actually a lot closer than either the left sum or the right sum. As a matter of fact, the midpoint sum and the trapezoid sum are, either one of them is better than the left or the right. Questions? I do not expect you to memorize this sort of formula. You'll be given it. Midpoint rule, see the xi stars? And it tells you on the end what xi star is. And then down here, trapezoid rule, 1/2 delta x, and then 1, 2, 2, 2, 2, 2, 1. Exactly like I wrote here.
How do you know though you can't do a derivative when you
Because what I started with trying to do that integral like for 30 or 40 minutes, hours, days, depending on the problem. But usually it's because I'm going to tell you. Here's the problem. Give me a numerical estimate. And again, I could use a lot more rectangles if I wanted a better estimate, right? My technology will do this. It may not do it directly. As a matter of fact, it's rather hard for me to get this to do it directly, but there is, on my calculator, in the math menu, way down at the bottom, you see that little arrow down there where it says 7? That means there's more options. If I keep going, I'll get all of this down there. And option 0 says summation. So I could go to option 0 and try and write the sum in this sigma notation. But that means I have to do the I like this, and I have to figure out how to write this xi in terms of our function, and that's not fun. So I don't like doing it on my calculator like this. But again, in that math menu, I see something a little bit above that summation that says fn int, a numerical integrator, function numerical integrate. The problem is, I don't know what method it's doing. I don't know if it does L or R or M or T. I don't know. What I do know is that it uses a crap ton of rectangles, as thin as the calculator will let me go. And the thinnest this calculator will let me go is 1 times 10 to the negative 12th. Teeny rectangles. So it does a whole crap ton of them. So I could say, integrate for me. It doesn't even write it in a weird way. It writes it like a definite integral, doesn't it? From 1 to 3, our function was e to the x squared dx. But I have no idea what it did. And that makes it the magic box, and I hate that. But if all I need is a number, great way to get it, isn't it? This is the equivalent of using Wolfram Alpha and saying, I hope it's right, but I don't know what it did. Questions? We did an under, and we only used 10 rectangles. It did something on the order of 2 billion rectangles, and it was therefore much more precise. But that's a question I could ask, how far off am I, right? So how could I figure out how far off I am? I could somehow try and figure what the midpoint or the trapezoid, how far away those are from the right answer. Well, it turns out, just like because you thought, hey, my graph is going up, I should be under if I'm on the left and above on the right, the concavity matters as to how I figure out how far off I am. So let's look at our second derivative. Now, this sounds like a very theoretical argument. I will do a practical example. I want to know how curvy does my function get between 1 and 3. I want to know if the second derivative can be bounded in some fashion.
How do you know what the value of k would be?
That's a very good question. I need to ask myself, what's the second derivative? So let's look at our function. F of x was e to the x squared. What's f prime of x? Congratulations, Maddie. I get to go back to doing derivatives.
2x e to the x squared.
Chain rule. Second derivative, therefore, requires the product rule.
Yeah, chain or 2 would be both.
Hold that thought. 2 e to the x squared plus 2x e to the x squared, and then the chain rule, another 2x. And I factored that for the moment just to make my life easier. Now, Jacob, our function was increasing, right? E to the x squared gets bigger as we go to the right. So between 1 and 3, I would expect this to be its biggest possible value at 3. What about this piece? Same deal, that's a line. And as we go to the right, that gets bigger. So I would expect this to be as big as possible when we get to 3. Say again? Yes, it would. Thank you. Which is still increasing, right? That's a parabola. It's still going up. Which means, Leo, if I want to know what's going on, what's a good value for K, I can put in 3.
You gotta take the maximum bound of the integral given.
Exactly. I want the biggest possible value I can get between A and B for F double prime. And in this case, that happens to be at 3. If I don't know where it is, that could be a problem. I can look at a graph, I can take my derivative, and I can try and figure out where that's equal to 0. But now I would say, okay, so F double prime of 3 is roughly what? Well, okay, that's e to the 9 times 2 plus 4 times 3 squared is 9. So that's 36, 38 e to the 9th, which is a really, really, really frickin' big number. What do I do with this number? Turns out that there's actually a computed error formula based on which test I'm doing. For the midpoint and the trapezoid rule. Oh, wait a second. The error for the midpoint rule, you take that number k that you got, you multiply it by the width of your integral cubed, and you divide by 24, and then the square of the number of rectangles. Notice that the trapezoid is less accurate than the midpoint. The error here is smaller than the error here because the denominator is bigger in this fraction. Now, where did this formula come from? It came from some of the stuff we'll do a little bit of in chapter 11. It came from series and sequence approximations of integrals. More on that later. For the moment, I'm going to ask you to trust me. I didn't make this up. But because our number for f double prime of 3 is so large, this error is going to be pretty big. We had done L10, right? So we were using 10 rectangles. Three minus 1 is 2. 2 cubed is 8. So the top of this is 38 e to the 9th times 8. We had 10 rectangles, 10 squared is 100 over 1200. 38 times 8 times e to the 9th divided by 1200. Yeah, my error was bigger than a lot, wasn't it? my error could be as much as 2,000. Which is why we came up with 800 and the calculator came up with 1,400. Yeah, that wasn't even close, was it? On the other hand, I could say, what if I wanted the error to be less than 100? Well, then I could say, I could up the number of rectangles because more rectangles gives me a more accurate answer. So let's find n. 38 e to the 9th times 8 over 12n squared less than or equal to 100. Well, if I move the n to the right side and divide by 100, I get 38 e to the 9th times 8 over 1200 less than or equal to n squared. Calculate this number on the left. Isn't that the number we just found, 2,000 and change, right? N squared must be bigger than or equal to 2,053. What's square root of 2053?
Like 45.31.
Then let's call it 46. If I wanted my error to be less than 100, I'd need to use 46 rectangles or more, right? But now I know in advance how close I have to get. I had to get within 100 of the answer. Maybe you want your answer to be within 1. Well, that's going to give me a lot larger of a number here, isn't it? If I want my answer to be within 0.1, I can keep increasing n to find this. By the way, this was based on the trapezoid rule. That's why there's a 12 on the bottom. If I use the midpoint rule, there'll be a 24 on the bottom, because the error on the midpoint rule is half the error from the trapezoid rule. Questions? No, in most situations, I'll be told what the maximum allowable error is. For example, we did back in the chapter on limits. So back in chapter 2, a long time ago, we talked about cutting a disc, and I needed to know what radius to make the disc exactly 1,000 square inches. And I need to know what the radius should be. And then I said, well, if I'm only allowed to be off by 5 square inches, what's my error? I'm producing rebar for concrete for buildings. I'm only allowed to be off by 1/10 of a millimeter in the diameter of my rebar. How close can I get? If for whatever this problem is, I'm only allowed to be off by 1, or I'm allowed, then how many do I need? Yeah.
So where did we put the above the 24?
That's the piece that I'm going to ask you to trust me on right now. That comes from the derivation we use in something called a Taylor series, which we'll do in chapter 11. But it's a way of approximating a function with a series, which is what we were doing here, and then looking at what's left over. And that's where that 12 and 24 come from, respectively.
Will it ever change?
No, those are stuck. If I change methods, it might change. But as long as I'm using the trapezoid rule or the midpoint rule, those are fixed. And they're on our formula sheet. The problem is that the midpoint rule requires me to do separate calculations for each of the data values, right? So it takes a little longer, and the trade-off for speed is accuracy. So I lose some speed, I gain some accuracy. And as a matter of fact, I can go even further in trading speed for accuracy. If I go back and look at that picture of the trapezoid versus the actual curve, there's a little bit of a curvature difference here, right? there's that little gap. So what if instead of using a straight line, I use something that curved, like a parabola? Well, if I use a parabola technically needs 3 points. You have 2 points, you try and draw a curve between them, you get a straight line. So to get it to bend right, I need a third point. So instead of just looking at xi and xi minus 1 to the left, I also have to look at xi plus 1 to the right. So that means I end up hitting some points much more than others. And a mathematician by the name of Simpson said, let's use curves at the top. Well, in that case, I end up hitting some of my points twice and some of my points 4 times. So it turns out I use the first one once, and then I start alternating 4s and 2s. And then the very last one only gets hit once. Then I need my delta x. So the delta x goes on the end here. But since I was doing this and hitting points more often and less often, I actually end up having to divide not by 2, but by 3. And in order to do this, n must be even. So I can do S10, but I can't do S9. I can do S8, can't do S9. Have to have an even number of divisions. Now, why would I bother to do this? Well, it turns out that the error for Simpson's rule is much, much smaller. Look at that bottom. 180 n to the 4th, not n squared. So more rectangles means a lot bigger of a denominator. And k changes here also. K is a bound for not f prime or f double prime, but the 4th derivative. So my error gets orders of magnitude smaller. Yes. My top gets bigger, but my bottom gets a lot smaller in the process. Again, I'll give them to you. But this version is substantially better. And again, I don't know what the calculator did to get its answer. It could have done left. It could have done right. It could have done midpoint. It could have done trapezoid. It could have done Simpson. It could have done one of hundreds of other numerical approximation methods. If this idea of getting better and better approximations to problems we can't solve directly is at all of interest to you, there is a course called Numerical Analysis next semester that literally solves problems that only can be solved this way, which show up in reality more than I would like. There's one other type of problem that I can address. We'll do that on Monday. And then that gives us 3 sections. That's the end of chapter 7. So Wednesday is question and answer day. And the reason I bring this to your attention is because Friday is exam 1, a week from today. And it covers all of chapter 7, and the review sheet is on campus right now. I will see you all. Have a wonderful rest of your day and enjoy your weekend.